So I'd like to start again by thanking the organizers, Jen, Yang, and Lucas for this workshop, and also for inviting me to my work. It's been great so far. I'm going to talk about circular photocurrents. It's great that I get to talk now after half of the workshop is done, because many of these things have been mentioned already. In fact, so many things have been mentioned that I feel like
more coffee break.
There will be some stuff that hasn't been mentioned. We have a new paper. So the old paper with the quantization prediction is this one. We have a new paper with a slightly different perspective on how to measure this, which is on difference frequency generation. I'll be talking about this, and I'm comparing two approaches. So I want to go a little bit deeper into the theory of how things work and what are the conditions to measure this experimentally. The idea is to bring this prediction as close to experiment as possible to see if it can be realized. And also towards the end of the talk, I will also mention that there are in fact two contributions to the circular photogalvanic effect in metals. There's an interband and an intraband or free carrier contribution that we didn't mention in the first paper. So there's some interesting stuff in this free carrier contribution as well. So the talk will be first part about the interband and then a little bit of free carrier at the end. So while semimetals don't need an introduction probably in this crowd, so I think Barry did a very nice job at the beginning introducing them. So for my talk, what's important is a file semimetal is any band structure that, or any material featuring file points in the band structure. File points are two-fold crossings of band energies, where at low energy the Hamiltonian is the Weil Hamiltonian that are called file points. They are characterized by being monopoles of the very curvature, so they're sources and sinks of very curvatures which are on the nodes like this. And so they are topological in the sense that if you build a surface around the node in momentum space and integrate the very curvature, because it's a monopole, the flux of the monopole to the sphere is quantized. So there's an integer that characterizes file point energies. So it's topological in a sense that is different from topological insulator. It's more like a local invariant in momentum space, but it's still quantized. And so one can think, in the same sense as in the Hall effect, one can measure the topological invariant of this state by measuring the Hall conductance. So one-to-one correspondence between Hall conductance and Chern number, the TKNN invariant. One may ask, can we do something similar or related for a metallic system, which does not have a gap, so the Hall conductivity is in principle not protected, that there might be something else that is quantized and that measures exactly this topological invariant. And as you know from several of the previous talks, we have this prediction that indeed there is the case that one can measure the Chern number of the file point in an experiment, and the type of experiment you do is circular photocurrent. You measure a circular photocurrent. So this is the punchline of the experiment. You shine circularly polarized light, and this produces a current. And this current, in the simplest expression or in the simplest model, looks like this. This is the degree of circular polarization of the current. So this is the imaginary part of E of omega. And the coefficient here is quantized in terms of fundamental constants only, the same thing as in the Hall effect. So there's P, E cubed, and H squared. And the coefficient here is the Chern number of the node. Okay? So there's a way of making the Chern number by doing this type of experiment. Note here I wrote a dTj, so this is not really a current, it's the derivative of the current with respect to time that is quantized. So it's a little bit different. And so what I want to do now is explain how does this work, how do we get it, how can we measure it. Okay? So the difference in this talk, what's new that is in this new paper I was mentioning, it's a different perspective to look at photocurrents, which is slightly different, so I'm going to try to connect these two. This new perspective or this new type of experiment is difference frequency generation, which is also a nonlinear effect. It's a bit more general. What you do now is you shine two beams with frequencies omega 1 and omega 2, and you still produce a current. Now the frequencies are different, so you usually for any nonlinear effect, output current is occurs at the sum of the frequencies that you shine. So for nonlinear process at second order. This is the general expression that one has. Because this has both plus and minus omegas, you get both frequency sum and frequency difference generation. I'm interested in frequency difference when the detuning is very small. So I take omega 1 and omega 2 as omega plus minus some very small detuning. Now I expand this function in the detuning parameter, and the resulting expression of what gets looks like this. Okay. So this is very similar to the photogalvanic effect. In fact, I'll connect in a minute. But you see that there are two contributions to the current that one makes. One is response to the circular light origin only, and so it has circular origin, and is proportional to sine of delta omega t, whereas the one that goes with linear polarization, which is this here, goes with cosine omega t. Okay, and so the what I've been calling the photogalvanic effect is the limit of this effect when the detuning goes to zero. When the detuning goes to zero, these two fields are the same, and you're really shining just one light and collecting the current. And then this crosses over to the photogalvanic effect. And so for the linear part, you can see there's no problem in letting delta omega go to zero. This just becomes 1. And this tensor here is the same tensor that one computes in the linear photogalvanic effect. But in the injection current, you can see something a little bit funny happens, because if I let delta omega go to 0, I get a t here remaining, right? So the sign at small argument is delta omega t, the delta omega cancels. So this becomes a current that apparently grows linearly in time. Okay, so this is an injection current. There's a more formal way of doing this. But if you just shine light and you have no dissipation, this is like the intrinsic process only, the current just grows linearly in time forever. Okay, and this is called an injection current. So in that sense, difference frequency generation is a way of regularizing this that you know, makes more sense, that you can keep shining light forever and it just oscillates with the sun at finite frequency difference. And in fact, this is an experiment that's probably hard to make, but conceptually it helps to do this calculation and to think about this problem in a way that is free of ambiguity. Okay? So the hypotheses that we use to derive this are, first of all, this is in the clean limit, so tau is formally infinity, the scattering time, so there's no scattering, so dissipation. This simple equation is only for the case of time reversal symmetry. If you break time reversal, there are more terms. And for now, I am only considering interband transitions, so there's no Fermi surface, even though Weyl semimetals always have a Fermi surface, but let me focus on interband pieces for now. And as I was saying, when delta goes to 0, this is photogalvanic. Okay? So in this way, I can, this will be eventually the next slide actually. So how do you measure different frequency generation? This is also a way of clarifying how this works. So if you have a current that oscillates in time now, because the detuning is finite, a current that oscillates in time radiates, so you can you don't need to collect the current in contacts anymore. You can measure the emitted terahertz field, which is this E out. And because of Maxwell's equations, if you have a current that oscillates, this E out is just proportional to the derivative of the current, and of course that's delta omega. So this is another way of distinguishing between injection and shift currents. If you shine a light that goes like this, then for the injection current for circular light, you get something that oscillates with the cosine of delta omega, the derivative of this. Whereas for shift, we get something that oscillates with the sine of delta. Okay? That's another way of seeing it. And this should be compared with the DC photocurrent, which is the limit when delta omega is 0. So if delta omega is 0, tau is going to be larger than this, so you're in the opposite regime, which is the you want the disordered regime, where tau matters. And so now it matters whether you're at short times or at long times compared to tau. At short times, as I said before, you get a current that grows linearly in time. But because now this is really DC, at some point the current has to saturate. So if you have some dissipation mechanism, the current doesn't grow forever, but it saturates at some finite value, which is proportional to tau. So this was our original prediction in the Nature Communications paper, and it has the problem that it has a tau sitting in front of it, and that's non-universal. That depends on details of the crystal or on the disorder potential in the crystal, and so the effect is not really quantized in this regime. You need to find a way of dividing by tau to have something properly quantized. And so what we said is, well, don't be in this regime, just measure this current really fast before it saturates, and then you're good. Of course, that's really hard. A better way of thinking about this is do difference frequency generation, where the beating is much faster than tau. So if you can achieve this, then you can distinguish between sine and cosine, and then picking out the cosine contribution is quantized and has no tau. Okay, so that's the new insight in the difference frequency generation paper. Okay, so this is general. I mean, this is not Weil semimetal, just theory of photocurrents. Now, why is this quantized in a Weil semimetal in particular? So for that, I need to show you a few lines of calculation for this beta coefficient. So beta is this guy here, right? So I'm going to take the trace of beta because this is a simpler calculation and it's essentially what is quantized in the end. So trace of beta means you shine light and you measure the longitudinal current in the direction of the applied light, and then you average over 3 directions. You do x, y, and z, and that's the trace of this tensor. So that formula for beta is written here. It has a simple interpretation in terms of Fermi-Golden's rule. So what's happening here is you have a resonant process between an occupied and unoccupied band. So you have some rate of excitation of electron-hole pairs. That's given by the optical matrix element R. So this is just R, the coupling to the electric field squared, the optical matrix element. So you have a rate of creation of electron-hole pairs, and then these electron-hole pairs carry a current, which is given by this term here. So the derivative of E is the velocity, and this is the difference in velocities between electrons and holes. So you average this velocity with the probability of excitation of electron-hole pairs over the Brillouin zone, and that gives you the photocurrent. Okay? And because this is a rate, this is also a rate of growth of current. It's not a constant current, but rate of growth. Okay? That's why this is a dTj. Okay? And so if you look at this equation for a minute, you see there's this delta function here picking up the resonant manifold, we call it. So the set of points in momentum space in K where you have a transition connected exactly by frequency omega. This defines a surface in momentum space. And you also have here the derivative of the same quantity that you have here as a function of momentum, right? So for that particular surface I defined, the decay of this quantity is the normal to this surface. Okay? It's the place where if the surface is like this, the derivative is the maximum gradient, which is the normal to the surface. And so this quantity here can really be written as just the flux of this optical matrix element through the surface that I just did. Okay, so this is a very simple way of writing this photogalvanic current, and that's all really. So now the one thing that I need to relate to Berry curvature is that this optical matrix element has the following sum rule for the Berry curvature. So Berry curvature of band N is obtained by summing R over the other index, over M. But now let's assume that frequency is very small, so that all the other bands that are not forming the Weil node are very far in energy, so that I can pretend that this is a two-band model, in which case I don't have a sum, I just have R12, the matrix element for this particular transition. And then R12 is essentially Berry curvature. Okay? And if that happens, then in this formula here, I just have flux of Berry curvature through this surface that I defined. And as I was saying at the beginning, the flux of Berry curvature is quantized over the Weil point. And so you just get the Chern number times this beta coefficient that I was mentioning. Okay? So if you have a two-band model, circular photogalvanic effect is quantized. What happens if the other bands are not so far away? Then this optical matrix element gets a correction. So now you just use this formula in reverse. So you solve for R12, and you find that there's an R13 as well. And so that also goes in here and screws up the quantization. But you can estimate how large is this R compared to omega, and you get this type of expression. So you see, but at low energies, E3 is the energy of the faraway band. The energy of this process is much smaller than E3, meaning the bands are far away. Then this decays like omega squared, and you can essentially throw it away. So there's a correction to quantization from higher bands. You're really probing the Weil point at low energies. This doesn't matter. This is the sense in which the circular photogalvanic effect is quantized. It's quantized when you're close to the node and nothing is quantized. So So this was the original prediction from the Nature Communications paper. You can try now how this works in a two-band model. There's one thing, if you've been in this field long enough, you immediately wonder, okay, you're measuring the Chern number, but I already know that in the Brillouin zone there must be an equal number of left and right nodes. So if I try this process for left and right nodes, it's going to give me the sum of opposite Chern numbers and it's going to cancel, and that is right. For example, if you have a mirror symmetry that relates left and right nodes at the same energy, then this effect has to cancel exactly. So what you need is that nodes at left and right nodes are not exactly at the same energy, and this does not have to happen in a system with no mirrors. Okay, so if you take a chiral system, where the lattice where the Weil semimetal is realized is chiral, it has no orientation reversing operations. Then the Weil points can be at any energy, and you may find a situation where one of the Weil points is Pauli blocked, so this transition doesn't happen, but the other one does. And so it's in that case where you can get a plateau. Now in the integral of the full Brillouin zone. Okay, so for example, if you take this band structure here and you take the chemical potential very near the node, let's say the green line, once you can make transition from here to here, you get something quantized all the way until the other node comes in and then it dies. Okay, so the chemical potential of the nodes matter because you need to Pauli block one but not the other one. So if you Pauli block both, it's 0. If both are active, it's also 0. So you need to find an energy window in between where the effect is quantized. Okay? And so the critical thing here is to find a Weil semimetal that's realized in a chiral lattice structure. And you know, tantalum arsenic, the famous one, doesn't work. And in fact, we don't really have candidates for Weil semimetals in chiral structures. This is the only one that has been predicted that would work, but this one that doesn't really grow. There have been no experiments since the prediction. But we can use it as an example to see how you know, the energy scales would work. So this is the band structure. It has nodes at different energies. This is neglecting spin orbit coupling, which is a good function for this material. So you have nodes that are separated by about 150 millielectron volts. And so if the frequency is is smaller than this, then you're activating this node but not the other one. So if omega is less than this energy but larger than 1 over the scattering rate, which let's say it's almost infinite, then there's a frequency region where you can observe quantization. If you put numbers in, I'm taking lifetimes from tantalum arsenic from this paper, but this is a big issue because you really need to know what tau is. But if you have a scattering rate of 4 millielectron volts between 4 and 150, you should have a window where you can measure the effect. Okay, and so if you want to know the number that you get from this combination of fundamental constants, you can write it like this. You can replace the electric field by the intensity of the light, and then you put it back in the equations, and you do this directional average that I was mentioning. And what you get is 22.2 amps per watt per picosecond. Okay, times the intensity, so the effect is linear. And so this is not just amps per watt, remember, because this is a rate of growth of the current, not just the current. Okay, so you either need to measure the slope, or stick a tau in, or do different frequency, all of these options that I was mentioning. Okay, so this is how it would work in this strontium disilicide, which does not exist. 4 years later, this material doesn't really grow, and we don't really have any other good candidates. An engineering one is hard because Weil points are, in principle, accidental. They can occur anywhere in the Brillouin zone, and there's no way to predict where they're going to end in general. So there is one case where we know how to make it work in chiral crystals, which is at trims. You have a, you know, all with spin orbit coupling, all two-fold crossings in trims in chiral crystals have to be Weil premium. And because they're chiral, they're not related to any other, so they can sit anywhere in the Brillouin zone. And this would be a very nice design principle to try to look for material that works. And this paper actually did a really good job in enumerating many candidates. But the problem is the splitting, because this is a spin orbit coupling effect, the splitting is very small. So the range in frequency where you could probe the effect is not really useful. So the bands for this case more or less look like this, right? So there's some type of Rashba splitting, but in 3 dimensions, and you want to make transitions like this. But this range is the energy scale of spin orbit coupling, which is small. Ideally, I want to have something big, like, you know, like this material. But this spin orbit won't get you this. So we don't have anything so far. So there was another option when we were writing the paper, which was these higher order nodal crossings, which have more than 2 bands. We actually had a referee asking this question: does this effect work for the multifolds? And so if you read the paper, you'll find we said no. This was me answering the referee and saying, you know, this thing is not expected to work, because essentially, if you take this correction I was mentioning before, this E3, the band that is far away, is crossing the node, so this E3 is 0. Okay, so this correction blows up, and it doesn't make sense. This will never be quantized. So this is what I answered to the referee and moved on, and I tried to design a valve semimetal in some other way. And then we found this, which came out a year later, which is another prediction for the multifolds that wasn't in the previous paper by Barry and co-workers. And they were not only predicting the band structure, but they tried the photocurrent calculation as well, and they found it's quantized at 4 because these nodes effectively have Chern number 4. Okay, and so I went back to this and I said, how does this work? And I was a bit puzzled for a while, but we thought, okay, let's go back to the blackboard and see what happened here, because in principle it should not work. But we were motivated to do it because, you know, we thought this might really exist. This might be the only candidate that we have, and really that's the case. So as you know, we've seen throughout the workshop in several talks, there are now a set of materials in space group 198 with the same structure that feature this threefold crossing with Chern number 4, cobalt silicide, and also aluminum platinum, as Niels was mentioning. The spin orbit coupling in these compounds is small in all of them, and you saw in Niels' talk that you have to work really hard to resolve the splitting. He has done it, so now we know that the Chern number is really 4. But for what I'm going to do, I'm still going to assume that there is essentially no spin orbit coupling here. Then I can tell what happens when you add it. Okay? But the material is there now. So let's see what happens with quantization. Does it really work? And so we were looking at this for a while, and it turns out it works, but it's kind of a fine-tuned thing. What happens is, now you have 3 bands, right? So you can have 2 types of transitions. Let's say chemical potential is above the node. So you can have the 1-2 transition. Let's say these are bands 1, 2, 3. This is the 1-3 transition. Here it's blocked. Higher energies, you can have both transitions. So now it depends. You have to compute both of them separately. In general, you have the flux of R2 through this surface and the flux of R3. So let's say I try to force this guy to be very curvature. So I can replace it by omega-1, but then I get one correction, which is this R13, as it happened before. But now the trick is I also have the 1-3 transition. This wasn't active in the previous case because the third band was really far away. Now it's not far, it's here. And if you write it like this is very suggestive, right? So it's actually the same matrix element, and the flux is through 2 different surfaces. And now comes the trick, which is in a linear model, you can prove, and thanks to Barry, we were working this together, and he had this insight that when this is linear, then you can prove that this flux is essentially the same for both surfaces, and it goes to 0, the correction. Okay, so in a linear model, when the dispersion is linear, all this goes away, and then you end up having the flux of very curvature, and so it's quantized. Okay, so in the previous paper, they showed this plot, but they didn't really show why it was quantized, or they didn't do the fine detail of what happens in here. In fact, depending on the type of transition that you have, you may have a plateau that is not quantized. Okay, see, if you only have the S12, you don't cancel this correction, and you have another plateau somewhere which is flat because the model is linear. There's no energy scale, but it is not quantized. So you need to go to the right range where all the transitions conspire so that this cancellation occurs. So we proved this also for 3-folds, 4-folds, 6-folds for all the classification. Okay, so there's always one window in somewhere, or at least there can always be a window where quantization happens, and it's exactly quantized in the linear. If the model is not linear, then it doesn't happen. Then there are corrections, okay, in addition to everything else. Okay. So in principle, cobalt silicide also works, okay, or all the the 198 compound. So throughout the talk, I've been saying many times, this only works if this happens, if that happens, if this energy is larger than this. So let me show a summary of everything that has to happen so that you can measure the quantized photocurrent. So first of all, you need to be in the regime where we call it the clean or the fast regime, where dTj is independent of tau. So tau is so large that essentially it doesn't matter. You can do this in two ways. I was going to put this first, sorry. So the first way is what I said, difference frequency generation. So when delta omega is much larger than tau minus 1, which means you're shining light, or say two beams with a beating that is much faster than tau. Okay? So if the beating is much faster, then you can resolve cosine versus sine, and then you can tell what is the injection and what is the shift, and there is no influence of tau. Then it's when it's really quantum. A related option that I haven't mentioned so far, but which is really the same, is instead of doing this beating, you just shine one pulse. And this pulse is again much shorter than tau. What happens in that case is, you will believe me, instead of sine and cosine, what you get is the shape of the pulse and the derivative of the shape. And you can tell the effect apart by just looking at the shape of the response. Right? So here you shine cosine and you get sine and cosine. Here you shine whatever else. You get this or the derivative of this, and you can tell this to things. In both cases, you need to be in the fast regime where everything happens before you saturate. Okay, and then tau doesn't matter. So that's one thing that you need to achieve. And then the other thing is you need the right window of frequencies. Okay, so I was saying you need to be in between the chemical potentials of the left and right nodes, so that Pauli blocking only blocks one node and not the other. Tau should also be, you know, almost near zero in the frequency scale. So this was delta omega, this is omega. This is usually not a problem in this energy scale. The problem is more the frequency here, because if you have, now this is the band structure of the multifold, and I want to do transitions here. I also have a band somewhere here. So there will be corrections in omega over this energy scale. So I put it here, and you have to be below that. Okay? And in addition, this is only for multifolds. If you're doing multifolds, there is also the quadratic corrections. I just said that this only works for linear models, but the multifolds are not linear. They do whatever in the Brillouin zone, so it's only linear around the node. So the quadratic corrections give you an energy scale. You have some effective mass from the bending, so m star Vf squared is an energy, and you also get corrections with this energy scale, so frequency has to be much smaller than this. And actually, for multifolds, this is going to be the critical drawback, because you can estimate this for this particular band structure. I think it's about 0.5 electron volts, so 500 MeV. So that's already, you know, the Pauli blocking here happens at maybe 0.4, 0.5, 0.6. But if this energy scale is much lower, then this doesn't really matter. What kills the quantization is this one. Okay? So there's, you know, there's a number of things that you need to make work properly so that this really happens. And in particular, because this is an extra drawback of multifolds, I would say it's still worth to keep looking for standard chiral vials that don't have this problem. Okay? Where the only problem is really the chemical potentials and that there are no other bands around. Something like strontium disilidride or something. Okay, I think it's still worth looking. So far, I mean, you've seen this experiment already. I think we'll also have more details in the next talk. But the only thing that is available so far is this experiment in rhodium silicon, where they have measured the circular photogalvanic effect. And well, it has this noise here, but it's in principle close to 4. It dies out where it should once the R point becomes active. You know, there's besides this noise here, there's also a few things in the way they did the theory for this paper that aren't quite right. So I think this is, you know, it's a nice first experiment that is showing that this can be done. I think that the matching to the theory probably can be done better. But let's keep in mind that because of the quadratic corrections, this isn't really quantized, properly quantized at any energy. Okay, so we asked Yang Zhang from Dresden, now at MIT, to do an ab initio calculation for us. And this is what happens in the absence of spin orbit. So this is at finite broadening, the calculation. So you see this step has some finite width, and there is also some residual. Is here at 2 minutes. Okay, that's good. I think I'll finish a couple minutes. So yeah, so This isn't exactly quantized, so again, experiment will introduce other errors, so this is still good enough, but you know, we have to probably keep looking for something better. And so in the last slide, last couple of minutes, let me mention this new free carrier contribution that we worked out so what I was doing is, let's just redo the theory for the full nonlinear response in general, as it's done in all of these papers. This has also been mentioned before. So you just want to redo this semiconductor theory for metals, assuming that now there is a Fermi surface. So the Fermi surface has a Fermi function that depends on k at the Fermi surface. And so this introduces a few changes in these derivations, but they're easy to keep track of. So you just do the same thing. It's a bit subtle, but it can be done. And what you find in the end is that in addition to the injection current and the shift current, there is a new piece that contributes to the circular photogalvanic effect that is only there for the Fermi surface. And it's circular, but it goes with the cosine. Okay? So it's more like this one, but it's circular in it. So the buried dipole that Inti was talking about as a circular contribution, that's in here, for example. Okay? So this is a Fermi surface piece. But what we found by doing this calculation to the end is that there are actually contributions beyond the buried dipole. So buried dipole is here. This is the buried curvature. There is also this semi-classical piece. So this the one that had three derivatives in Inti's talk, if you integrate by parts and put this derivative here. But there is also this new piece that has an energy denominator. And this is not semi-classical, this is not of semi-classical origin, but it's still there. And because it has this energy denominator, it's going to give spikes in the circular photogalvanic effect. And this had been missed before, or at least, I mean, we didn't know of it before. But this formula was actually derived in Genkin and Metnis in '68. In this paper with this very suggestive title, right? Nonlinear effects with partially filled bands. And I found this paper only after doing the derivation, but here it is. So buried dipole, if you want, was already anticipated in '68 in the field. And so I'm not going to go into the details of how this is derived, but let me just point out that there is a very close connection between this free carrier difference frequency generation and the linear polarizability. In fact, you can see these two equations are almost exactly the same. If you take the reactive part, which is this, the only thing that changes from the reactive linear polarizability to this is that I switch f by the derivative of it. That gets me one more index, so this has three indices now, but everything else is the same. So for every piece in linear polarizability, there is a free carrier photocurrent. For example, the anomalous Hall effect gives you buried dipole, the Drude peak gives you this semi-classical guy, and the interband piece gives you this, this new spiky configuration. So these are my results. Again, this is Yan Sang doing the prediction. This is the one I showed before. This is the prediction for rhodium silicon or tantalum arsenide. You can see these spikes at the places where you get the onset of new transitions. And so one should really take this into account when interpreting circular photogalvanic experiments. And since I think I'm out of time, let me just thank my collaborators in this project and also discussion with other people related to the subject, in particular Ivo and Inti Sodeman, Bing Hai, Liang Wu, and Niels here in the audience. And yeah, the collaborators, Rolf Grusin, Joel Moore, and Takahiro at Berkeley, Barry, and Felix Flicker was at Oxford, Maya in Spain, San Sebastian, and Niels and Emerson. And so with this, I'll finish and take questions.
The next person should set up. Who is it? Right. Yeah. We should start to set up. Okay, so we have time for maybe one question. While he sets up. I have one quick thing to point out. This material that Barry talked about earlier, this tantalum, this Weil CDW, it's chiral. Right. So the high temperature phase has lots of Weil points everywhere. So you might want to look at that. I mean, there's lots of Weil points and like they're very narrowly separated, but it is a conventional Weil semimetal.
Right. And a chiral crystal. There are no other, you know, the thing is that the band structure looked really nice in the high symmetry lines, but what Barry was telling me is that there's a bunch of other stuff.
There's like almost 50 Weil points all throughout the bronze zone.
If you have bands on top or below, then that is good. But yeah, it's worth looking.
But it is an example at least.
Another potential example could be if you took one of the multifold fermions and then applied a symmetry breaking field to like split a spin 1 Weil into like two you know, when you split them, the chirality still has to be there, so you know we'll split into 2 vials. Maybe this could be a way to engineer the vial points that you're looking for.
It's already chiral to
Maybe.
start with.
It's already chiral. You know, the dispersion one might have a lot of
Yeah, that's a
remnants
good
of being
point. Yeah,
nonlinear.
Yeah.
Okay. Let's thank the speaker again.